I wanted to build a robotic arm from scratch. I did it, but things didn't go smoothly. I bought some cheap servos from Amazon. On paper, they were pretty powerful, but in reality, they were a huge letdown. To redeem myself, I am doing this the right way. This will be the first video in a series where I systematically go through the process of building a robotic arm. It won't just be a summary. It will be a complete breakdown of the robot building process. Let's start by defining what a system actually is. We can think of a system as a black box. It takes an input, performs some calculation, and produces a result. For our robotic arm, voltage is the input, and the position of the arm is the output. We can define this system using either a differential equation or a transfer function. Let's look at the equation. GFS represents the physics that describes the arm, and UFS is the voltage provided to the motors. Multiplying them gives us the final position. That weird L is just a cheat code, the Laplace transform, that lets us convert a complicated convolution into simple multiplication. It's fine if you don't understand the math fully yet. The key takeaway is that GFS describes our plant or system, and our goal right now is to figure out what GFS is for this arm. We start by building a free body diagram. Here, theta 1 and theta 2 are the angles of the servos, L1 and L2 are the lengths of the arm segments, and M1 and M2 are the masses attached to the arm. The equation of motion for many mathematical systems can be written in the form of Euler-Lagrange equation. Simply put, force is equal to the mass matrix plus the centrifugal and pyrolysis matrix plus the conservative force like gravity. Now let's go ahead and define all the functions. First, we define our states. These are theta 1 and theta 2. Our outputs are the forces, also torques. We use the matrices provided in standard robotics textbook to calculate all the physical forces. Writing this in the matrix form just makes life easier. Then we identify our system, in this case our robot, and plug its specific parameter into the matrices that we just set up. This gives us everything that we need to mathematically describe our two-joint robotic arm. Now we can build a simple simulation. Keep in mind, this model does not include the actuator dynamics yet. It is just simulating the physics of the two joints and the external forces acting on them. In the next video, we will model the actuators to get even more realistic results. For now, I have a simple simulation running. It tries to hold its position but fails. It's nowhere close to perfect yet, but I just wanted to give you a sense of what the math is actually doing.